Hello, Coach Travis here with another calculus video. So what we got here is a really interesting problem, and it's kind of crazy when you first read it, like what is it asking for, what's going on, but it is a really interesting problem. So what we got here is it's asking us we got a function. It looks like we got a function, x is the input, but then we got a couple variables in the function. So it's a piecewise defined function, and it's got a couple of unknown values, a and b. And so it says determine the values of that a and that b that make the function continuous and differentiable at x is equal to -2. So, okay, so we see that, yeah, at -2, that's where the piecewise defined function where it splits, and so that's probably where crazy things are going to happen, and we need to pick the a and the b so that this entire function we need to find specific values for a and b so that when you put them in here, this function will be both continuous and differentiable. So what the heck is going on with that question? So it's really helpful, I think, to look at a picture of what's going on. So here's the idea. So here's the left part of the function. So the left part of the function is just a straight line with slope 11. And so but it stops, remember it stops when x is equal to -2, because -2 was the place where the piecewise defined function changed. So the left part is just a straight line, no problem there. And then the right part is a parabola, but we can change the values of a and b. So like right now, the b is 3.5, but I can change that value. Like in the original problem, we see that the a and the b are allowed to change. So we can change the a and the b. So right now, the way it stands, obviously this function is not continuous at -2. But maybe if I move b down to maybe where, I don't know, about right at -13, if b is -13, it looks like maybe the two pieces match up, maybe. Because, you know, looks can be deceiving, but it looks like they kind of match up. And so now the function's continuous, but wait a minute. Oh, but it's kind of, if you look carefully, it's kind of got a corner there. It kind of has a corner, you know, it's not smooth. The way the functions attach to each other right there, it's not smooth. And so we know that to be differentiable, you have to be smooth. So we can make it continuous, but that didn't make it smooth. So rats. So maybe but wait, but not so fast. I can change a. So as I change a, that's going to change the shape of the right side. And so maybe if I change a to, I don't know, maybe if I change a to -5.5, and well, now it's not continuous. Oh, but wait a minute, I can still change b. So I'll change b and maybe make b -2. And okay, so now where they connect, right here at -2, where they connect, it's an improvement. But again, I can't tell. If I zoom in a whole lot, maybe it would not, maybe I could see a corner. Maybe there's a very small corner right there that it's hard to detect with the naked eye. But anyway, that's kind of the idea of the question, is by playing with the values of a and b, we can not only make these two functions attach, but what we can do is make them attach in a perfectly smooth fashion. So that's the challenge, is try to find the values of A and B so that the two functions attach in a perfectly smooth way. So, okay, so what a great question. So let's try to see how we're gonna figure it out. So, all right, well, so what are we gonna do? We gotta think about continuity, and we have to think about differentiability. So when I think about, so first I'm gonna think about continuity. And so when I think about continuity, I think about limits. And in particular, when I think about limits, I think about the limit from the left and the limit from the right. So what I'm gonna do is I'm gonna figure out what the limit of this function from the left is. So I'm gonna have the left side of the screen here, and I'm gonna have the right side of the screen here. So on the left-hand side of the screen, I want to ask myself, well, what is the limit as x goes to, and I want x to get close to -2, because -2, that's the point that we're interested in. So the limit as x goes to -2. Oh, but I said I wanted this to be the left-hand limit. So I'll put a little negative sign there to denote the left-hand limit. So I want to ask myself, what's the limit as x goes to 2 from the left of f of x? And if I think about that, well, that's going to be the limit as x goes to -2 from the left. Oh, I got to fix that. That's some pretty sloppy handwriting there. -2 from the left. And so if I'm working with the left function is this one right here. So that's the function I'm going to use. So it's going to be 11x plus 5. And so now the way you can compute this limit is you can just plug in the -2. And so that gives you, let's see, -2 times 11 makes -22, and -22 plus 5 makes -17. So that is what, that's the limit from the left. And okay, and then, and actually, oh, well, no, we'll go ahead and just go forward here. So now I want to do the right-hand limit. So I'm going to look at the limit as x goes to -2 from the right this time of the same function. Okay, but this time, since I'm approaching from the right, I'm going to use this function, because this is the function that you use when x is greater than -2. So when x is on the right of -2, you use that second function. So all right, so this is going to be equal to the limit as x goes to -2 from the right of -x squared plus a times x plus b. And then now we can set x equal to -2. So it's the, and again, it's the x that's being equal to -2, not the a or the b. The a or the b, I don't know yet. But if I set x equal to -2, then I get -4 minus 2a plus b. All right, so then, so what? What does this mean? Well, what this means is in order for the function to be continuous, if I want the function to be continuous, then we know that the limit at x equals 2, -2, the limit at x equals -2 has to exist. And the only way the limit can exist is if the limit from the left and the limit from the right are the same thing. So those have to be equal. So, all right, so I got an equation. So I have a clue as to what A and B are. So I know that, aha, so I know that -4 minus 2A plus B has to be equal to -17. And I guess I could add 4 to both sides, and I get -2A plus B is equal to -13. All right, so I've got that. So that's so I got good news and bad news. So the bad news is that I'm not done, because this is one equation with 2 unknowns. So I can't solve this for A or B. I don't have enough information. So I need more information. In other words, I'm not done with the problem yet, because I don't have enough information. So we got to figure out, well, gosh, how am I going to get more information? Well, let's see. I'll let you, yeah, while I'm erasing, you can think about how am I going to get more information? I'm going to leave this here because we're going to need that later, but I want to erase everything else. So how we're going to get more information is this differentiable part. Is we haven't used the fact that we want these to be differentiable. So that we want this function to be differentiable. So differentiable means that the derivative exists. So the derivative has to be an actual number. And so, okay, so let's think about what the derivative of this function is going to be. And again, it's going to depend. There's going to be a left side and a right side, right? Because let's move this down a little bit here. That from the left side, the derivative will be the slope of this part. And from the right side, the derivative will be the slope of the right part. So there's going to be sort of a left-hand, there's going to be a left-hand derivative and a right-hand derivative. So once again, we have to look from the left and from the right. So we're going to have a right-hand side and a left-hand side. So this will be from the left. And okay, so let's see. So what's the derivative on the left-hand side? So I guess I'll put an L here for left-hand derivative. So we usually don't talk about left-hand and right-hand derivatives. This might be the only time this semester that we ever consider this. So this is sort of non-standard notation, but we'll use it for right now. So, well, again, if I'm looking at the left-hand part of the function, I'm going to look at this part. And so you think, well, what's the derivative of that part? Well, if you use the constant multiple rule and the constant rule, you can see that the derivative is just going to be 11. Because the derivative of x is 1, and the derivative of just the number 5 is 0. And you know, another way to think about this is, remember, derivative is slope. The derivative is slope, and this is a straight line. This is a line with slope 11. So it's no surprise. You can use fancy formulas to get that the derivative is 11, or you could just think about it and say, well, hey, this is a straight line with slope 11, and the derivative is the slope, so the derivative has to be 11. All right, so from the sort of the left-hand derivative is going to be 11. Oh, whoops. I made a little mistake. I mean, it's not important. Oh, sorry, I didn't do anything wrong. But what I should have written here was a -2. Because that's really what we care about. We care about what happens at -2. We care about what's happening when x is -2. So what I wrote was still correct because this line always has slope 11, no matter what x is, as long as x is less than -2. But what I really care about is what's the slope at -2. Okay, and now let's look at the right-hand slope. So for the right-hand derivative, so the derivative on the right, let's see, so I'll say f prime, and I'll put a little r for right. And I want to have negative, well, actually, wait, but you know, I'm going to go ahead and put the x there again. You say, well, wait, wasn't that a mistake? Well, yeah, but I think it makes it more clear. So we'll do it for x, and then we'll put in -2. So we'll find the derivative function, and then we'll set x equal to -2. So all right, so if I find the derivative function of this, then let's see, well, you can use the power rule and the constant multiple rule to get -2 times x, because the 2 comes down in front and multiplies by the -1. And then you get plus, all right, the derivative of x is just 1, and a is a constant. So using the constant multiple rule along with the power rule, why did I write a 1? Then you just get a. Oh, I know why I wrote 1. I wrote 1 because the derivative of x was 1. And then I'm going to have a times 1. And so we'll just write a. So that's and then the derivative of b, well, b is a constant. So the derivative of b is 0. So I won't even write it down. All right, so there's the derivative from the right. And now we can plug in -2. So fr of -2 is equal to, okay, so again, I'm setting x equal to -2. So a -2 times a -2 makes a +4. And then the a is just a, right? A is this constant that I have no information about yet. So that's what I've got now. So what happened there is I replaced everywhere I saw an x, I replaced it by -2. And so -2 times another -2 makes a +4. Okay, but now we're in the same situation we were before, that if we want this function to be differentiable, then that means that the derivative from the left at -2 and the derivative from the right at -2 have to be the same thing. So we've got another equation here. We've got that, what do we have here? We have that 4 plus a is equal to 11. All right, and now I think we're in business because, so let's get rid of all of this. Okay, so yeah, that second equation, that blue equation, if 4 plus a is equal to 11, well, that's not too hard to see that that means that a has to be 7. Okay. And now, what my other equation, my red equation, was -2 times a plus b has to be equal to -13. Well, but we now know that a is 7. So I can put a 7 in for a. So if I put 7 in for a, I get -14 plus b is equal to -13, and then that, it's not too hard to see. I could add 14 to both sides, so I get b is equal to 1. So all right, so my final answer is a has to be 7, and b, actually, let me write it off to the side. Let's see, or I'll write it, where should I don't know where I should write it. Wherever I have room. My final answer is a should be equal to 7, and B should be equal to 1. And then what we should always do is check that our answer makes sense, because it's possible maybe I made a mistake somewhere. So I want to check, does my answer make sense? And you'd say, well, yeah, how am I supposed to check my answer? And what you can do to check your answers, remember we got GeoGebra here. We can look at the picture. So we can play around here. And so let's see what happens. Let's set A equal to 7. So A is equal to 7. And now we'll set B equal to 1. And poof, look at that. There you go. They fit together. And the mathematics tells us that they fit together in a perfectly smooth, that is, the way that they join up right there is perfectly smooth. They completely match slopes right at that join point. So, all right, so that's how you do problems like that.